Titration of a polyprotic acid. So the example here is sulfurous acid being titrated with sodium hydroxide. Polyprotic acid is weak in both of those. So the first ionizable hydrogen comes off with a Ka of 1.6 times 10 to the minus 2. The second one comes off with a Ka of 6.4 times 10 to the minus 8. So if there's enough difference between those two Kas, like there is for this one, then on your pH curve, you'll see two equivalence points that are distinctly separated. So you've got two separate curves. If those Kas are too close, it'll just kind of meld together and it'll be hard to distinguish. In this example, for the concentrations that were used, it took 25 milliliters to reach the first equivalence point. It will take the same volume to reach the second equivalence point, because 25 milliliters to get rid of the first proton and 25 to get rid of the second. Any questions? So titrations can be monitored with either a pH meter or an indicator. So until Tuesday, you had probably only done indicator titrations, phenolphthalein, and looking for the pale pink. Then we did the pH meters, which in some ways that's nicer, and in some ways it was a real pain, wasn't it? So we're going to talk about the indicators here. So with the indicator, we're looking at the color change. And that point where the color changes is called the end point. That's the end of the titration. We would like the end point to be the same as the equivalence point. The equivalence point is where you've got a stoichiometric amount of sodium hydroxide added. So here's an example. I think this is probably phenolphthalein. So we're adding frustration because this is just, this room doesn't like me. Okay. Are we working again? No. Fine, whatever. I'll point on the screen. So here we've got the phenolphthalein being colorless. And then when we get to this equivalence point, the indicator begins to change, and then past that equivalence point, then we've got a very bright pink indicator.
And that's what we did earlier.
Yeah, that's what we did for that rough run to just figure out, well, how much of my unknown acid should I weigh out? We did a titration to figure that out using phenolphthalein. So what are these indicators? Well, indicators are weak organic acids, and they have a different color as an acid and as a conjugate base. Phenolphthalein is shown here, very common indicator. Here's the acid, which is colorless, the acidic form, and the basic form has a very intense pink color. Because the color is very intense, we only need a little tiny bit of the indicator, and so that's not going to affect our titration. If you needed a lot of phenolphthalein, then you're adding another acid into your titration. It's going to mess everything up. So these things have very intense colors. And here we see phenolphthalein in different pH buffers. We can see at 7, it's clear. In this pH 9, it's just turning pink. And in pH 10, it's intensely pink. So the indicators will change color within a range of about 2 pH units, and that'll be centered at the pKa for that weak acid. So when the pH of the titration is equal to the pKa of the indicator, you're going to get an intermediate color. If it's below, you're going to have, if it's above, you're going to have the color of the base, and if it's below the pKa, you're going to have the color of the acidic form. So this is a different indicator, methyl red, and so it is sort of a purplish red down here, and it changes around pH 5 and then becomes yellow. So this is a chart showing different acid-base indicators, and they're arranged here in order of their pKa values for the most part. And so you can use this chart to select an appropriate indicator. So if you're titrating, an acid, a strong acid, you don't want to use something like crystal violet, because that's already going to have changed color before you even start the titration. And you wouldn't want to use something like alizarin yellow down here, because that's going to change color way past your endpoint. But those are useful for other things.